Yeah, comes on everyone. Let's start off. And then last thing that we did was this. Okay, let's go ahead. Let's do a few more on this and so let's say we have a wall here. Coefficient of restitution is E. This is also E. You projected a particle with speed u and theta. This particle flies and hits the wall at the highest point, and then it bounces off onto the ground. And then from here again, it will bounce and go back to the point of projection. So a ball is projected with speed u at angle theta. It collides with the wall perpendicularly. Basically, that will be your H max. Perpendicularly and bounces off the ground and goes back to the point of projection. Find the coefficient of restitution. Find E. E is same for the wall and the floor. Let's get this. Try. Ishpan, you know how to do, na? Or you just remember the answer? Try it again. Na? See if you're getting it or not. Just do it in rough and fast. Because exam what will happen? They'll change the equation. They will say this distance is r way for it. Hit like this, not at the perpendicular. Then you'll be gone. Yeah. Next we had it. So when you're hitting at the H max, what is the speed? U cos theta. So if you hit the H max with U cos theta, you'll bounce back with what speed? E times EU cos theta, isn't it? So let's see this thing. So first of all, you're hitting it perpendicularly. So during a projectile motion, if you're hitting it perpendicularly, that means this distance must be r by 2, half of the range. And you're hitting the wall with speed u cos theta. And we know if you hit the wall with speed u cos theta, you'll bounce back with the speed of eu cos theta. Everyone agrees with that? Now, since they're at the same height, now tell me one thing. If your speed becomes e times, then where will you land on the ground? Both of them will have same time of flight. So you will land at a distance of er by 2. Is that clear, everyone? Are you getting why it will be e times, this thing? Because see, what is the formula for range? So when you're throwing from a building, the range will be the horizontal velocity ux into root over 2h by g. So in both the cases, the height is same, right? Because this height is same for both of them. So the range is proportional to ux. So when the speed is u cos theta, you're traveling r by 2. If the speed is eu cos theta, then you'll travel e times r by 2. I hope that is making sense. Is everyone clear with that statement? Next thing. So now when you come and hit the ground, now what happens? Now when you are hitting the ground, remember your velocity, right? The horizontal component has become eu cos theta. So when you come back to the ground, the vertical component will be u sin theta. Remember, restitution is still e only. So now after collision, the ball will bounce back again, but this time the vertical component becomes eu sin theta, and the horizontal component will remain same. We have seen this in oblique collision. If the ball collides with the floor, only the vertical component will change along the normal, the other component remains same. Is this clear, everyone? So this is the collision with the floor. That means this ball, which is bouncing off, will have vertically the speed becomes eu sin theta. Horizontally the speed is eu cos theta. This flies like a projectile and lands somewhere here. What is the range? So the time of flight will be 2v vertical by g, which is 2 eu sin theta by g. And what is this new range? Horizontal velocity, which is eu cos theta into time of flight. If you substitute the value, you will get e square r. Yeah, just
Recording in progress.
yeah. Someone switched off the Wi-Fi. Just give me a minute. Yeah, the Wi-Fi is back. Clear? Able to hear me, right? Okay. Okay. So this thing goes back to E square R. So you're done. So basically R by 2 must be equal to E square R plus E into R by 2. R will cancel. You get half is equal to E square plus E by 2. You get E square 2E square plus E minus 1 is equal to 0. So E is equal to minus 1 plus or minus root square 1 minus 8 by 2. This will be minus 1 plus or minus 3 by 2. So we get E is equal to minus 1, minus 2, or half. Minus 2 is not accepted, so E is equal to half. Check. Clear with this? So first time when you hit the wall, you will come back only E times R by 2. And after hitting the floor, your vertical component became E times, horizontal also became E times. So you will travel E square R. So this total distance must be equal to R by 2. Then you get a quadratic and you're done. Is that clear, everyone? Any doubts on this? Clear? Let's see one more. It's a good one based on projectile and oblique collisions. This is another one. Velocity of the ball before collision let's call it u bar is 3i plus 4j. After collision, the velocity v bar becomes 2i minus j. Find quotient restitution. So this ball is colliding obliquely with something. We don't know exactly how it is. Matlab, the ball might be something like this. The ball is colliding like this and bounces off like this. Something is happening. That's it. We only have this information. You have the initial velocity and the final velocity before and after collision. Using this information, find the quotient of restitution. Think it's a good one.
So it's colliding with what?
It's something. It's colliding with a wall or a floor or something. It is just a ball, no?
Okay, so the other thing is not moving, right? I mean, it's
You
fixed.
want something like that. Velocity of the ball before collision, after collision with the fixed ball. Happy?
Okay.
Hmm. Now, how is the ball? We don't know. It is at an angle. How do you handle that? Listen, the thing is, we know whenever you collide with a wall or something, only the component along the normal changes, right? That means, suppose if the wall is like this is your normal vector, let's call it n cap. And your ball is coming with some speed, this is u bar. After a collision, it bounces with speed v bar. Okay? Now, we know that during the collision, the force will be along the normal. Since force is along the normal, so acceleration is also along the normal. Since force is along the normal, the change in momentum, delta p bar, is also along normal because F is dp by dt. Right? So therefore, delta p is nothing but mass into delta v. So delta v bar is also along normal. This is how you can find the normal ka vector. You don't need to know how is the wall. So what is delta v bar? Delta v bar is v bar minus u bar, right? Which you can subtract here, which will be 2 minus 3 minus I cap minus j minus 4j minus 5j cap. This is your delta v bar. So delta v cap will be minus I cap minus 5j cap by root 26. This is also the direction of the normal vector. Because delta v cap is along the normal, so the unit vectors must be same. Clear with this? Everyone understood how we got the normal vector? 3 by 23. Let's see. Might be the answer. Any doubts on this concept, everyone? The change in velocity must be along the force. And when you're hitting the wall, how is the force? The force is along the normal. That means the change in velocity ka vector and the force ka normal vector must be in the same direction. If two vectors are in the same direction, they're parallel vectors. That means their unit vector must be same. So delta v cap and n cap are equal. Clear? Once we got this, now, so we know this. So whenever you collide with the wall, this is u bar. Let's check if I take this angle to be theta. So this component will be how much? So this will be u sine theta. And this will be u cos theta. This we have done in oblique collisions. So only the component along the normal will get reversed, meaning it will become e times. So after the collision, this velocity will remain u sine theta, so which is v bar. This component will become v, whatever is this angle, phi, v cos phi. And this is v sine phi. So we can clearly see, so that means whenever you're hitting with a u cos theta, after the collision, you'll bounce back with eu cos theta, which is v cos phi in this scenario. So there, so coefficient of restitution is nothing but v cos phi by u cos theta. Do you agree with this? So the ratio of components along the normal will give you the coefficient of restitution. So I don't want v, I want v cos phi. I don't want u, I want u cos theta. So how do we get that? So if this is your normal, This is your u bar, and this is theta. I hope you remember a bar dot b bar is mod a, mod b, cos theta. So mod a cos theta is a bar dot b bar by mod b. You guys remember that concept? Vector component of one vector in the direction of another vector. Will it does in dot product. So using that same logic, so if you want a u cos theta, this is nothing but a u cap dot n cap. It should be minus n cap, but okay, we'll just take the magnitude by mod n cap. That's your u cos theta. Similarly, v cos phi will be v bar dot n cap by mod n cap. I hope you remember this thing, vector components. Component of one vector in the direction of another vector. So you're done. You got everything. Therefore, E is equal to V cos phi by U cos theta. So this is nothing but a V bar dot n cap. Mod n cap is anyway 1 in the denominator. By U bar dot n cap. We'll put a mod because we just want the magnitude. Now you can simplify this further. V bar, and what is n cap? N cap is nothing but delta V bar. Delta V cap. This will be U bar delta V cap. This is V bar minus U bar by mod V minus U bar by U bar minus dot V bar minus U bar by mod V bar minus U bar. The denominators will cancel. That will become V bar dot V bar minus V bar dot U bar. U bar dot V bar minus U bar dot U bar. This becomes V square minus V bar dot U bar by U square minus I guess we'll put a mod anyway, so it doesn't matter. U square minus V bar dot U bar. There, everyone. So you can just simplify the whole thing in terms of just U bar and V bar. Again, what did we do? This is the first thing you need to understand. The velocity will change along the normal. And that means delta V bar must be parallel to the normal vector. I know initial velocity, I know final velocity. From there, I can find the change in velocity. The unit vector of change in velocity must be the unit vector along the normal. Because when two vectors are parallel, the unit vectors will be same. Then what we did, whenever you're hitting a wall, only the normal component will reverse. So if you hit with speed u, you'll come back with eu. So if you hit with u cos theta, you'll come back with eu cos theta. So eu cos theta must be v cos phi. So E is nothing but the ratio of the final velocity along the normal by initial velocity along the normal. So what you want is actually component of velocity along the normal. How do you find component of one vector in another vector? In case you forgot, you should go back to vectors and check it out. We have done this in dot product. You have not used this till now anywhere, but now we are using it. If you remember, we have done these questions. This is a vector component of one along the another vector, the projections. Page 149. You got u cos theta and v cos phi. So divide them, you'll get v bar dot n cap, and n cap is nothing but delta v bar by mod delta v, which is v bar minus u bar by magnitude of the vector. I substituted there, denominator this guy and this guy will cancel. That's just a magnitude, and then you're done. So there, now you know everything, b square, u square, everything, you can substitute here. How much you guys are getting? Someone said they got 3 by 23. So you can check your answer. Now it is just a matter of doing a dot product and square. Is that clear, everyone? It's a good one. So there, this would be your generalized formula in terms of u and v. You can remember, great, or else you know how to derive. Any doubts on this? Anyone not clear with any particular step here? All clear with this? Next one. Next one. Clear now, Vedika? Utsa, got this? You got the answer anyway, right? Shaurya? Clear? Devanshi? Aditi? Ovia? Clear? Ishman? Clear with this? Arya? Arya, are you there?
Yes, sir.
Yeah. Clear with this? Next thing. Top view. So it's like your carom board. So we have a coin here. Striker, mass is 2m and radius is r. So this is going horizontally. Here we have two coins. This mass is m, radius is also r, mass m and radius r. So this velocity is exactly like this. E is the coefficient of restitution. So this guy will come and hit the coins, and you know what will happen? The coins will fly off at an angles. Find the final velocities after collision of the striker and the two coins. The coins ka mass is m and radius r. Striker ka mass is 2m, but radius is also same. So find the final velocities. Let's get this. Right. How will you handle this? First of all, figure out what is the angle just before collision. Hmm. Did you guys get the final picture? Always draw your final picture. So just before collision, they will be like this. And if you join the centers, you can clearly see they will form an equilateral triangle. So this angle will be 30 degrees. This angle will be 30 degrees. I hope everyone got that. So just before collision, this guy is going with speed u. Yeah, I'm just separating them a little bit. And how is the force? The force will be along the common normal. That is a line joining the center. Here the normal would be like this. Again, I'm separating it out. So this is also 30 degrees. So this is before collision. So let me draw it here better. So that means how will the forces be? The normal reactions will be in this direction. That means after the collision, these two balls will fly away along the normal. Think about this, because you're hitting them along the normal. There is no other way. You will gain velocity in this direction. Let this be V2. Let this be V2. And this guy will go in V1. These are your final velocities. This is after collision. The two balls will fly along the common normal car direction. So they'll go at angles V2 and V2. This is 30 degrees and this is 30 degrees. So there, this is a picture just after collision. So you need to find V1, V2. If you do that, your job's done. Try. How will you do that? So just when they're about to collide, the angles are, they'll form an equilateral triangle. The forces will be along the normal, which is the line joining the centers. So if you see, the striker will still go in the horizontal direction, because the normal and normal, it is symmetrical. The force is still in the net force is in the horizontal direction. So the striker will continue to go horizontally. We don't know whether it is going front or back, but it is going horizontally. These two balls will fly away at an angles of 30 and 30 degrees with horizontal. This much we know. Just after collision, picture will look like this. What do we do in collisions? We conserve momentum and we use quotient restitution. So let's do that. Okay, let's see. So first thing, we'll conserve horizontal momentum. Because there are no external forces, momentum is conserved in every direction. So initial momentum will be, this guy is traveling with the speed u. The mass will be 2mu. The big ball ka mass is 2m, m and m. That will be 2mv1 plus mv2 cos 30, 2 times. 2 goes off, m goes off, u is equal to v1 plus v2 cos 30. That's your equation 1. Next thing, how will you use quotient restitution? Now, if you guys remember, what is E ka value? E is the quotient restitution. These are the velocities along the normal, and you apply it only for two bodies. Restitution is applied between two bodies in collision. You don't apply for all the three bodies at the same time. So this is u1 bar minus u2 bar. These are velocities along the common normal. These are not the net velocities. That means you should resolve the velocities. So this u ka component will be u cos 30. This is your u1, right? And this v1 ka component will be v1 cos 30. This is your v1 bar. So you have to apply the restitution for the components. So E is equal to V2. That will be, this is the normal. So that is V2 only. V1 bar, that will be V1 cos 30 by U1, that is U cos 30. Initially the ball is at rest, so 0. So we get V2 minus V1 cos 30 is equal to EU cos 30. This is your restitution, everyone. If you apply the restitution between these two balls, you still get the same equation. So it is same. Please have a look at equation 1 and equation 2. That's it. If you got this, your job's done. Just a matter of solving now. So remember that coefficient restitution is used only for two bodies at a time. You don't apply restitution for three bodies. And the velocities must be taken always along the normal. You don't take the full velocities. So you should take the initial velocity of the ball in this direction. You should take the final velocity of the striker in this direction, and you have to do restitution for that. I think, yeah, you got everything. So then it's just a matter of solving. You'll understand why I'm giving in terms of u. Because there'll be a question like this. Find the value of E if the striker goes back. Find the value of E if the striker always keeps moving forward. So they'll ask options like that. V1 plus V2 cos 30. Second thing will be V2 minus V1 cos 30 ZU cos 30. Great. So V2 will be V1 root 3 by 2 EU root 3 by 2. Take this, substitute here. So U is equal to V1 plus V2 will be V1 cos 30 is again root 3 by 2. 3 by 4 plus EU 3 by 4. This would be U into 1 minus 3E by 4, 7 V1 by 4. So V1 will be U by 7, 4 minus 3. Check. That's your V1. And then V2 will be number bad. You can solve this. You'll get V2 value from here. Everyone got V2? And you can clearly see actually, since E is always less than equal to 1, V1 is always positive. V1 always keep going forward, obviously. V2, let's solve actually. क्या करें? U minus 4U by 7 minus 3EU by 7. That is 3U by 7, 1 plus E, 2 by root 3. I think you get something of this sort. I missed something here. U minus. Okay. That looks. Yeah, that looks right. Clear with this. So if you see, since E is always greater than equal to 0, V2 can never become negative. So the striker will never go back. But anyways, got the two equations? All clear with this? This is an important one. It's a pretty standard question. These are oblique collisions. Let's see one more. Then we will go ahead to variable mass system. This came in last year advanced question, and this is something which we every year do it. It's a standard question. People who remember, they just went and just marked the answer. So we have a big ball here and we have a small ball here. Initially, it is at rest. This big ball is coming with speed u. The collision need not be head on. Getting it? It's an elastic collision. Right. So just to show you the picture. So after collision, what happens? This ball, right, will fly away. So let's say this is M, this is U. It is coming and hitting this ball. Something like this. It's an oblique collision. So after collision, your big ball started going away in this direction, and your small ball is going in some direction like this. Let's call this thing V1, let's call this thing V2. This angle is theta and this angle is alpha. So they basically deflect. You're getting it? So this is after collision. The two balls will fly away in two different directions. This is before collision. This is the picture. We don't know exactly where you're colliding and everything. So the question is, find the maximum value of theta, right? Find the value of capital M by small m for the maximum angle deflected. Or let's simply keep it like this. Find max theta. So basically, I'm asking you to find maximum theta. There, that is the question. You should remember the result, but let's see how to derive this. Try. I'll give 2-3 minutes. Are you getting the question? If you hit head on, the ball will just go straight. So there is no deflection. There is no angle theta. So if you hit at some angle here, this will just fly off at an angle. So the question is, what is the maximum angle you can push it out? M is greater than small m. That information you need. Hope the question was clear. This came last year. We are doing this from so many years. Last year it popped up. That is what happens. Questions do pop up once in a while. Not because we are guessing or something. We do so many models, something will come. This is lengthy though. And this will not be the first time you'll be seeing this kind of problems. We will see again these kind of problems in different chapters called modern physics and everything. Meaning, I'll show you one. This would be the last chapter. You actually have problems like this. So our neutron is coming in colliding with the nitrogen atom and they fly off at different angles. So questions will be framed that way. Show you one more. There, something similar. A neutron collides with a helium atom and the helium flies off and the nitrogen goes up perpendicularly. Oblique collisions basically. That's what I'm saying. Don't think what you're learning is only in this chapter. They will pop up in some other chapter in a different form. So how do we do this? So let's see. There's a lot of working involved, so that's the reason I'm telling you. Remember the result, it helps, but know how to solve also. Because this will come in different forms. Anyway, we know only two things, conservation of momentum, and since it's an elastic collision, conservation of energy. So horizontal momentum. Mu is equal to small m v1 cos theta. You take only the horizontal component plus m v2 cos alpha. Vertical momentum initially is 0. So finally it should be mv1 sin theta minus capital mv2 sin alpha. That's your equation 2, right? So here what we can do, we can square them and add them. If you square them, then you get what? This would be m square u square. That will become, we need to actually eliminate alpha. I don't want alpha because you want to find theta, right? So let's do that. mv2 cos alpha is mu minus mv1 cos theta. mv2 sin alpha is mv1 sin theta. So now if you square them and add them, alpha will go away from the picture. And left hand side will become m square v2 square. The right side will become mu minus mv1 cos theta ka square. There are other ways to do also. You can stand in the center of mass frame and do, but okay. You get this thing, right? You can expand this further. M square v2 square, m square u square, m square v1 square cos square theta minus 2 mu mv1 cos theta plus mv square v1 square sin square theta. Sin square theta cos square theta, that becomes again 1. You can send away that m square on that side. This will become v2 square. This will become u square. This will become m square by capital M square. Cos square theta sin square theta is 1. That's v1 square minus 2 u m by capital M v1 cos theta. There. Hmm. Perfect. This is your equation 3. Next thing, conservation of energy. Again, remember we are trying to find that cos theta there. What is initial energy? Half m u square will be equal to half m v1 square half capital M v2 square. So I can eliminate my v2 there, right? So half goes off, you end up with let's write this thing directly. v2 square will be half will go off, that will be u square minus m by m v1 square. That is your v2 square. And this is your equation 2. Equation 4. Now take this equation 4 and dump it in the equation 3. That will become u square minus m by m v1 square will be u square m square by m square v1 square u square goes off. Did I miss something here? Hmm. Interesting. That thing got cancelled. This thing, if I shift it here, I'll get V1 also. One V1 also got cancelled. This was not expecting. Think I goofed up somewhere. I still have U left here. I don't want that. It will become lengthy actually. I didn't simplify it properly. Let's just check the equations again. Horizontal momentum is mu is equal to, ठीक है. I think I got the mistake. I did something completely wrong. You're not asking maximum angle deflected by small m. You're asking maximum deflected by capital M. There, that was the mistake. I did completely something different. The question is find maximum alpha, not the small one. That thing can deflect anything, whatever it wants. That was a mistake. You have to find alpha. That means I can't eliminate alpha. I want alpha. mv1 cos theta is mu minus mv2 cos alpha. Square them and add them. Story is still the same. LHS will become m square v1 square. This will become m square u square plus m square v2 square cos square alpha minus 2m square u v2 cos alpha plus m square v2 square sine square alpha. Shit, Ray. This entire thing went off. So this will be how much? M square v1 square, m square u square, cos square alpha sine square alpha becomes 1. That's m square v2 square, 2mu square u v2 cos alpha. Perfect. Then we get this v2 square is this. So you want to eliminate any one of them. Let's eliminate v1 or v2, it doesn't matter. So v1 square will be m into u square minus v2 square. This is equation 4 and this is equation 3. So take equation 4 and dump it in 3. That would be m square m u square minus v2 square. There, you get something of this sort. Bring all v2s together. There's a small m there. We should try this in the center of mass frame. I think that would be still lengthy, might help you with one or two equations less. Oof. Perfect. There, we got all V2 square, so bring them all to one side. So V2 square will be m square plus m small m minus 2m square u cos alpha v2 plus m square u square minus m u square is equal to 0. This is a quadratic equation in v2. I know, pretty lengthy and messed up. That's it. I totally remember the result. Now here on v2 is the velocity of the ball. So after the collision, the ball will keep going in some direction. So v2 has to be real. Therefore, discriminant delta must be greater than or equal to 0. So the discriminant delta will be 2m square u cos alpha ka whole square minus 4a, which is m square plus mm. I hope I didn't go for any calculations. M square u square minus mm u square must be greater than or equal to 0. So if you solve this, you should get something. Take what m common here. Take what u square common here, and one m also common here. That will be m minus m. U square goes off, m goes off, 4 also goes off. You are stuck with m square. Cos square alpha is greater than m square minus m square. Bring it this side. So m square must be greater than or equal to m square into 1 minus cos square alpha. You get m square plus m square will be less than or equal to sine square alpha. So we get sine alpha must be less than or equal to m by m. Therefore, the maximum deflection is, so max alpha is sine inverse small m by capital M. Phew, that's your result. There, do remember the result. It did come in 2025 advanced version. So when I taught this that time also, your seniors said like, oh, such a big thing. Who will do in the exam? And it came. You never know. The result is pretty good to remember. So play with this. Check out the working. Right? It is lengthy. Just try it on your own again. Take a break. Come back in 5 minutes. We will continue from here. So next thing, we will start off with variable mass system. What happens if the system ka mass is changing? Any doubt so far? Chal, come back in 5 minutes. Yeah, chalo, camps on everyone. Chal, let's start off. Camps on. Next thing is your variable mass system. This we did have a small discussion, on this thing in Newton's second law when we did NLM. Remember the trolley was going, rainwater is falling, what happens and all that. So let's say this. Let's say if you have a body of mass m, which is going with a speed v, and let's say at the same time someone is also applying a force on this. So this is your initial condition. So during this process, let's say it ejects a small particle. Consider a body moving with speed v, which ejects a small mass dm. Its speed u relative to the body. Means with respect to the body, you are throwing with the speed u. Then when you throw this body, so this thing is like, remember the man jumping from a plank wala problem. The mass of the system becomes m minus dm. Others, you need to keep your cams on. Brakes over. This is F external. Because the particle is thrown out, your speed will change, v plus dv. And this small dm particle, remember, u relative is the speed with respect to the body. But the speed of the body became v plus dv. So your speed becomes v plus dv plus u relative. Hope you remember when the man jumps from the platform, it is a speed with respect to the new speed of the platform. This is the scenario after the particle leaves. Is the picture clear, everyone? So the particle is actually going out with the speed u relative to the body, but the body itself is going with the speed of v plus dv. So when the particle is thrown out, the speed of the body changes. Now, don't worry, dv can be negative or positive. The science will take care of it. If you throw it back, it will go faster. If you throw front, it will actually go slower. Then we use the Newton's second law. What is Newton's second law? Force is proportional to rate of change of momentum. F external is dp by dt, which is p final minus p initial by dt. So p final here is the body plus the particle. Again, a little more calculations. M plus dm into v plus dv plus this is m minus dm plus dm into v plus dv plus u relative minus m into v. That's your final momentum minus initial momentum by dt. When you expand this whole thing, we'll get mv minus m dv dmv minus mv. You know, today it is all a lot of terms today. This guy and this guy will cancel. This guy and this guy will cancel. This guy and this guy will cancel. So you're just left with m dv by dt plus u relative dm by dt. So there, this is your force kata. Now this is important. This thing actually looks like the second law of form, but there's a small variation here that u is the relative velocity here. So there are two components here. This m is the mass of the body at time t. dv by dt is the acceleration of the body. ur is the relative velocity of the mass ejected from the body. dm by dt is your rate of change of mass. Ejected with respect to body. So if you see this thing actually looks like m dv by dt plus v dm by dt, but that v is not the velocity of the body, but v relative there. Now we will simplify this in a much simpler form, which is usable. So don't worry about this. Clear with this? Now this equation, what happens if there is no external force acting on the body? If F external is 0, so let's say on that body there is no external force acting, then you get 0 is equal to m into dv by dt plus u relative into dm by dt. So this will become m into acceleration. This will be minus u relative into dm by dt. So this m into a is what we call as thrust force. So there, you can remember this. So we define something called thrust force. This is simply the force because you're ejecting the particle out. It behaves as if there is a force coming because of the ejection. So here, the negative sign indicates the thrust force is opposite to the velocity. I'll give an example what it means. Opposite to ejection. So if someone asks you, right, what is the force thing, you can actually simplify this. You can simply write this thing as F external plus F thrust force is equal to mass into acceleration. There, this will make your life easy. You need not do all those calculations and everything. You can simply treat when you're ejecting a gas from a rocket or something, you can assume as if the rocket is being pushed by an additional force called F thrust. So, example, let's say we have a rocket and let's say it is ejecting gases. Let me show it on the next page, but you can put it up. Thrust force, that's a quite an important result. See, let me show you an example. So let's say we have a rocket here. Rocket ejects 10 kgs per second of hot gases. With a speed of 200 meters per second. They'll give you something like this. Find the acceleration of the rocket when mass of the rocket is 1000 kgs. Right? And assume neglect gravity. So this is how you do. You draw your free body diagram. Because the gases are coming out, this will generate a force called F thrust. That's it. You can just ignore all that thing with F thrust and you're done. F thrust is how much? Again, we're taking the magnitude. Because the gases are coming this way, U relative opposite to it. So the minus sign is taken care, which is U relative into dm by dt. U relative is 200 and dm by dt is 10 kgs per second. So that's like 2000 newtons. And it is given mass of the rocket at that time is 1000 kgs. Therefore, acceleration of the rocket is F thrust by acceleration 2 meter per second square. Clear with this? So all that rocket propulsion, you can just replace it with one equation called F thrust and you can just solve the problems normally. Is that clear, everyone? So let me ask you one more like this, an easy one. Let's see, you tell me. So let's say we have a rocket on the ground. Gravity is there this time. Mass of the rocket is, let's say 1000 kgs. The gas is being ejected. So this is the scenario at t is equal to 0. The gas is ejected at a rate of 20 kgs per second. With let's say 300 meters per second with respect to rocket. So the first question, find the time when the rocket lifts off. So rocket immediately won't go off. You have to, overcome the weight. And find acceleration of the rocket. At t is equal to 30 seconds. There, let's get these two. What is Newton's third law, Srihari? No, just tell me one thing. Can you derive this using Newton's third law? Please do that. You can't, nah. That's the result. Yeah. The third law simply says what? Because the gas is being pushed out, it goes forward. Ho gaya. That's the reason, na? When your gas is pushing out, the force is forward. Let's get this. This would be simple mains level equations. Find the time when the rocket lifts off. And at t is equal to 30 seconds, what is the acceleration of the rocket? This time gravity is there, g is equal to 10. Okay, 20. Right, Samyak. Get this, everyone. You should try. Ishman, wo nahi hai answer. Try it again. Chalo, chalo. Everyone should try. Why? Everyone is so dull and tired today. Something happened. It's 11th November, so there's nothing today also. Is it because Children's Day is coming? Something of that sort. You started realizing you're not a kid anymore and you don't have an holiday for Children's Day. Okay, we got 2 there. 50 Nero. So 50 is too much. It's a sad realization. Your college will say you're not a kid anymore, they don't give you a holiday. But your mom and dad will say you're always a kid to us. And they don't let you do what you want. So, there. Okay, let's see. First of all, understand one thing. Mass of the rocket is also changing. What is the thrust force? F thrust, again, I'm taking the magnitude, U relative dm by dt. You are ejecting with a speed of 300 meters per second, and every second you're ejecting 20 kgs. So this rocket is actually generating 6,000 newtons or 600 kgs ka force. So if you draw the FBD of the rocket, we have thrust force pushing it upward. That is the best thing. Once you're at thrust force, you can just forget about all that thing. And your gravity weight is acting mg, right? And yeah, so if you want to lift off, F thrust must be greater than or equal to small mg. That means 6,000 is mg. So m must be less than or equal to 600 kgs. That means you should burn off. Therefore, 400 kgs of fuel must be burned off. Someone overloaded the rocket. Until the weight of the whole rocket becomes 400, 600 kgs, the rocket won't lift off. And how much fuel are you burning every second? 20 kgs per second. So therefore, the time will be, you need to burn 400 kgs of fuel and you're burning 20 kgs every second. So it will take 20 seconds for the rocket to lift off. Are you clear? So you overloaded the rocket. So the rocket won't lift off until you burn off 400 kgs of fuel. Now what about the second part? Obvious is 25. Anyone else got 25 for the second part? What is the second part? Find the acceleration of the rocket at 30 seconds. Now be careful. 30 seconds में rocket का mass also changed. So in the second part, acceleration will be up. At t is equal to 30 seconds, you have burned 600 kgs of fuel is burned. Therefore, the mass of the rocket is 400 kgs. So the remaining fuel plus rocket is 400. So this is 4,000. And this must be 6,000. And the mass is 400. So you're done. F thrust minus small mg is equal to small ma. This will be 6,000 minus 4,000 is equal to 400 into A. So A will be 2000 by 400. That is 5 meters per second. Check. Is that clear, everyone? So this is what actually happens to the rocket. As the mass gets over more and more, you actually go much faster. So when a rocket is launched, it actually goes with an increasing acceleration. Easy question. Everyone got this? Check out the calculations. Anyone not clear with anything, please ask. Let's see one more. Clear now, yeah? Got your mistake? Next one. Same thing, but let's say this time. So we have a rocket here. T is equal to 0. M is the mass of the rocket plus fuel. Gravity is there. The gas is being ejected with the speed of u relative. Right? And gas is ejected at a rate of lambda kgs per second. Right? Find the speed of the rocket at time t. The rocket lifts off at t is equal to 0. So the moment you start the engine, it lifts off, means you have enough thrust force. Find speed of the rocket at time t. There, let's get this. This you have to indicate, everyone. Because as you're going, mass is changing continuously, so your acceleration is changing. So A is not constant. How do we start? Draw your free body diagram after time t. After time t, your mass of the rocket will be m, which is m minus lambda t. Isn't it? That is the amount of rocket fuel burned. For time t, fuel burned. Remember, every second you are ejecting lambda kgs per second. So your lambda kgs ka mass is decreasing. Will be lambda into t. So this is the new mass. Interestingly here, the thrust force remains constant. So in a rocket, when it is going, it's not the thrust force that changes, the mass gets messed up, which will be u relative into dm by dt, which is lambda. So this is u relative into lambda. Remember, ur is constant, lambda is constant. So if you observe there, if the gas comes out faster, the rocket ka thrust force actually increases. That's the reason. If you see the rocket ka the exhaust, they design it like this. They make this thing little narrower. So when the gas tries to push through, it comes out much faster. Did you ever play with your water ka tap? If you close half of the tap, what happens? The water comes out faster. So they try to make it, thinner so that the gas comes out much faster. You get more thrust force. And same time, remember your gravity is still acting, which is small mg, and your acceleration. That's it. So the entire, mass changing and ejection, you can just put thrust force and you're done. Nesh Mantera, I think you messed up the limits. You got the main idea though. F thrust minus small mg is equal to small m into acceleration. This is u relative into lambda minus, this will be divided by small m. So small m minus g is equal to acceleration. So we get acceleration is equal to ur lambda by m minus lambda t minus g. A is nothing but dv by dt. Send dt that side. dv, this will be ur lambda integral dt by m minus lambda t minus g integral dt. Hope you remember this integration. You have dx by ax plus b ka integral is 1 by a ln ax plus b. I told you this is important, keeps coming a lot. This limits will go from 0 to v, this limits will go from 0 to t, this limits will go from 0 to t. LHS will become v, this will become ur lambda. So if you see a ka place mein we have minus lambda, so minus 1 by lambda ln m minus lambda t, limits will go from 0 to t minus gt. Lambda lambda goes off, we get minus u relative. Put t is 0, you will get ln m minus lambda t. Put t and put 0, you'll get minus ln m minus gt. So your final answer will be v is equal to u relative ln capital M by m minus lambda t minus gt. This is your velocity of the rocket at time t. Have a look at the steps. So once you wrote this, then it just becomes max after this. Yeah. So if you neglect gravity, let's say the rockets are in space, if gravity is neglected, then your v, velocity of the rocket, becomes u relative ln m minus lambda t. So finally, when the rocket ka fuel gets over, the final speed of the rocket after all the fuel is burned. So if you have a rocket in a space, and if you burn down all the fuel, then what is the maximum speed you can get? So the v final is u relative ln, this capital M is the initial mass of the rocket, or you can simply say this is the initial mass by m minus lambda d. So once all the fuel gets over, you have final mass. So I can write like this also. This will be ln mass of rocket plus fuel by mass of only the rocket after the fuel gets over. So it actually depends on that ratio, how much fuel you have and how much rocket ka mass is there. And that is the reason to maximize the speed, you actually prefer to increase UR. So it depends on the load ka ratio. For example, if they tell you like this, right? The rocket has 500 kgs fuel and the payload is 500 kgs. That means maximum speed is UR ln 2. Are you getting with that? There have been questions like that in CET or main. So example, let's say the payload is 1000 kgs and let's say the fuel is 9000 kgs and let's say U relative is 300 meters per second. So this rocket in gravity-free space, the final speed will be 300 ln, the total mass will be 10,000 by 1000. So that would be 300 ln 10. That would be the maximum speed of the rocket in that example. Okay with this? All clear with this? There, that's about rocket propulsion. So questions should be of this sort. So whenever you see rocket propulsion, just replace that entire gas going out and all with F thrust. Just draw your regular FBD and solve. You will get the answers. There. Yeah. That. Let's see one more. Let's say we have a trolley and on top of this trolley, there is a lot of sand. Capital M is mass of the sand plus trolley. Now what you did, you started applying a force F, which is a constant force. You are applying a constant force on the trolley. At the same time, maybe there's a small hole at the bottom. The sand starts leaking out. And basically, it falls on the ground and it starts leaking. I could also say it's a big water tank and water is leaking. So same thing, it works. Sand is leaking at a constant rate of lambda kgs per second. Now see, if the sand had been constant now, the acceleration will be constant, your life would have been easy. So this is the scenario at t is 0. Find the velocity of the trolley at time t. Initially at rest. These are all the questions where the mass is changing. If the mass had been constant, you would say F is equal to ma and you're done V is equal to U plus AT. It looks scary, but if you actually put that equation, this one, F external plus F thrust is ma. Try, I'll give you 2 minutes. It just looks scary, it is actually easy to solve. You'll get this in like 5-6 steps. How do you handle this? Let's write the equation. F external, because the sand is leaking, there might be a thrust force, we'll see about that, is equal to mass into acceleration. Okay. Let's talk about the F thrust first of all. Now here, look at this. When the sand is coming out, let the trolley ka speed be V. So the sand which is on top of it, when the sand is leaking vertically here, can you tell me what will be the speed of the sand? Let's say if you're sitting in a bus which is going at 50 kilometers per hour, and if you jump from the bus, what will be your speed? Same speed as the bus, isn't it? So when the sand is leaking out, it is not coming with zero speed. The sand is also coming out with the speed V only. Getting it? So the sand which is leaking will have the same speed as the trolley at that instant. So when you take an object and you just drop it from a moving vehicle, you will have the speed of the vehicle, will have same velocity as the trolley. Therefore, U relative is zero. Implies there is no thrust force. Is that clear, this everyone? There's no relative velocity between them. You're just dropping it gently, so nothing will happen. You don't get any pushed or anything. F thrust is zero. And what about the mass? Mass at time t, I think let me take this as small a, will be small m, will be capital M, the initial mass, minus how much sand is leaking, lambda into t. So F external becomes F. This thrust force is zero. This is m minus lambda t into acceleration. So we get dv by dt is equal to F by m minus lambda t. So we get dv is equal to F into dt by m minus lambda t. Integrate this 0 to v, 0 to t. We get v is equal to, this will become minus F by lambda ln m minus lambda t. Limits will go from 0 to t. This would be F by lambda ln m by m minus lambda t. So I send the minus sign inside and you substitute the limits. That's your velocity of the trolley after time t. Is that clear, everyone? If you send the minus sign inside, ln will reverse. Na? Ln a by b becomes ln b by a. If you want, I'll show you that. So this is minus F by lambda. This is ln m minus lambda t minus ln m. Send that minus sign inside. This will become F by lambda ln m by m minus lambda t. There, I was skipping that step every time. Is that clear, everyone? Same question. There's another variation of this. I'll keep them together so you will understand. Let's say we have a trolley. It's a long trolley. Someone is pulling with a constant force. F is equal to constant. M is the mass of the trolley. So So somewhere here we have a container which is filled with sand. So this sand starts falling on the trolley and sticks. This is reverse. So sand is falling onto the trolley at a rate of lambda kgs per second. Almost zero speed, it just gently falling and sticking. Find the velocity of the trolley starting from rest. Both are similar. In one case, the sand is already there, you're leaking. Second case, sand is falling onto the trolley. This question is exactly the same question as this. Remember this question? A trolley is pulled with force F and rainwater is collected at a rate of lambda kgs per second. Find the force required to maintain the speed. The second question, find the speed of the trolley at time t. This was something like this. It's the same question basically. Then I taught you can actually use momentum and finish it off. So we did a variation of this. There it was rainwater, here it is sand. That's the only difference. Now listen the difference between this and the previous one. We will write the equation again, same thing, F external plus F thrust is equal to MA. Now, listen carefully here, F thrust is not zero. After some time, the trolley will be going with some speed V. The sand particles which are falling, the speed of the sand particle is zero, isn't it? That's sticking. So what is the V relative? So velocity of the sand with respect to this particle is minus V, where V is the velocity of trolley. So the trolley will think, if you stand on the trolley, you will think the sand particles are actually going backward, isn't it? Previous question, both had same speed. So here V trolley was like this. Are you getting the difference between both of them? So here V relative is not zero. So this is a V of the trolley at time t. So your F external will be F minus U relative, which is the opposite thing, which is minus V dm by dt is equal to m into A, where m will be m plus lambda t. That's the catch. So because of the sand falling, the thrust force will actually act backward. So the trolley will think it is slowing down, something is pulling you back. So there is a V relative now. This is F minus V into lambda. This is m plus lambda t into A. A is nothing but dV by dt. Bring all V's to one side and dT's to one side. This will be dt by m plus lambda t. This will be dV by F minus lambda V. Integrate on both sides. This will go from 0 to t. This will go from 0 to V. This is 1 by lambda. That is m plus lambda t. Yeah, 1 by lambda ln m plus lambda t 0 to t minus 1 by lambda. This will be ln f minus lambda v 0 to v. Lambda goes off. This will become ln m plus lambda t minus ln m minus ln f minus lambda v minus ln f. M plus lambda d by m is equal to ln f by f minus lambda v. You can equate the terms inside. Mg plus lambda t by m is equal to f minus lambda v. Then so lambda v will be f minus fm by m plus lambda t cross multiply. Fm will cancel. You end up with f lambda t by m plus lambda t. V is equal to ft by m plus lambda t. Clear with this? There's a much faster way to do this instead of doing all this. Alternatively, you could have just argued like this. Force is dp by dt. So integral dp, change in momentum, is integral f dt. So change in momentum is simply integral f into dt. What is change in momentum? M final, v final, minus m initial, v initial. This will be f into t because f is constant. Final mass is m plus lambda t. V final, initial mass is m, but initial velocity is 0. Therefore, we get V final is f into t by m plus lambda t. The same answer without integration. But unfortunately, this will not work for this problem. When the sand is leaking, you can't apply that thing. So there, if you want integration, you can do this. Both are good ones. Huh? The reason together they're good ones, because most people get confused between two both. Here if you see F thrust is 0 because V relative is 0. Here F thrust is not 0 because the sand is falling with negligible speed. So V relative is 0 in the horizontal direction. Have a look at the steps. All clear with this? So there. So both the cases, sand leaving the trolley or sand falling on the trolley. Clear, everyone? Aditi? Advai? Shreyan? Clear? Trishi? Ashvi? Devanshi? Clear? Let's go ahead. Chain problems. So let's say we have a heap of chain. So here we have a heap of chain. So someone is pulling this chain outside with a constant speed f. Neglect gravity. Chain is pulled out of the heap with speed v. So there is a big chain ka heap there, and you started catching a chain and you started pulling it. Find f. Neglect gravity. So with how much force should you pull so that the chain comes out with constant speed? Standard question. Let's see how will we do this. See, you can use that formula and do. There is also a faster way. Imagine a small part of the chain comes out. Let this be dx. So what is the mass of this small part? Lambda into dx. So dx part is coming out of the chain. So what is the change in momentum here? So dp will be dm into v. So this part is coming out with speed v. So force is equal to dp by dt, which is dm by dt into v. And dm is nothing but lambda dx. And what is dx by dt? Velocity, lambda v square. It's a pretty good result. Remember this. That means whenever you want to pull the chain out of the heap, you have to apply a force of lambda v square. Right, Aditya? So if you see here, the speed is not increasing, but because the mass is continuously increasing, so you could have done with the equation also. F external is m dv by dt plus v relative dm by dt. So this is f, this is 0 because speed is constant. V relative is u and dm by dt is that term only. There, you could have done that one, it works. So if you want to pull the chain out of the heap, you have to apply a force lambda v square. Clear with that? Let's see a variation of this. Let's say we have a chain. But this time someone decided to pull the chain vertically up. You're applying a force F and the chain is pulled vertically with you. This time gravity is also there. And the chain ka weight is lambda kgs per second. The chain is pulled out vertically with a constant speed u. And let this distance be x. X is the height of the chain pulled or length of the chain pulled out. Find the power due to the external force. So how much power is this force generating as function of x? Find the power due to F external as function of x. What is power? F into v. So you can ask a lot more on this, but let's get this first. So as you're pulling the chain out, the weight of the chain is increasing. Your F is not constant. Let's see how you handle that. Let's draw the FBD. So this vertical chain, which is x, how many forces are acting? One, you're pulling up with F external. Second, you have your own weight mg Third, you're pulling with the force of lambda v square, Newton's third law. If you pull the chain out of the heap with lambda v square, the chain will pull you back with lambda v square. This is the force on chain due to the heap. So every time you pull the chain out of the heap, you have to apply lambda v square. Just give me a minute. Let me take the attendance. So people are just leaving randomly without informing. You just call your parents and ask them what's the reason. Yeah, Ma'am is calling them. Perfect. Great. And remember, you're going with a constant speed u, so acceleration is 0. So the external force will be small mg plus lambda v square. And what is small m? Lambda into x. Lambda is the mass per unit length and x is the length of the chain. There, you're done. So F external is lambda x g plus lambda v square. There, the force is increasing continuously with x. And what is the power? F external into v. That's lambda xg plus lambda v square into. And if you notice here, if you look at the energy of the chain, that will be potential energy plus kinetic energy. This will be mg x by 2, because you have to take the center of mass, plus kinetic energy will be half m v square. This comes out to be lambda g x square by 2 plus half lambda x v square. This is the energy of the chain at any instant. So if you want power, so if you differentiate this, d by dt, you get lambda g by 2, this is 2x, and dx by dt plus half lambda v square dx by dt. This comes out to be lambda gxv plus half lambda v cube. This is actually the power basically on this chain. This is the power chain in the chain. If you observe something here, you don't get the same answer. You get a difference of half. So this is the power present in the chain. Basically, this is the power the chain is getting. Whereas the external force is giving you lambda gxv plus lambda v cube. See the difference there? So that means whatever energy you are giving, all the energy is not coming out. There will be heat produced. The chain actually starts getting hot. Power external minus power retained, that will come out to be half lambda v cube. So when you're pulling the chain, all the energy is not getting acquired by the chain. The reason, think of this. So when you're pulling the chains here, now see, this chain is there. Initially, the speed is 0. So I'll call this thing chain 1 and chain 2. The next moment when you pull this, we had this discussion, I and Arya had this big discussion on this one day. So this guy becomes 1 and this guy becomes 2. So it's like a perfectly inelastic collision. Suddenly from v, it has gained speed v. And when this thing collides with 1, so it's like whenever the chain link is moving, right, it's like a perfectly inelastic collision. So every time it collides, there is a loss of energy. So they can ask you that also. How much power are you giving? How much power are you retaining? The remaining becomes heat. So in this scenario, the whole chain starts becoming warm. So every time you pull the link suddenly moves with a jerk. So it gains speed and then suddenly becomes constant. So it's like a collision continuously. It's a good one. There, that's about the chain. So with that, we are done with the chapter. We have done almost 57 questions. So please make sure to go through the whole thing. On Thursday, when we catch up, we'll start off with rotational mechanics. Right? I already sent you some sheets on this, Vijika sheets. Those are good. You can try them. Right? They're only like 25 questions. So first of all, make sure to go through the notes. Notes itself is your biggest revision. We have 57 questions there. So work on that first and start solving your material. Please don't delay anymore. Right? Try to finish off this in another 10 or 10 days maximum.